Right, this evening we are very privileged because we have Ed Cherry, who is a world recognised expert in amplifier design and related technologies, but not just amplifiers. Ed has a very deep and capable knowledge in electronics, semiconductor devices, unified charge control theory, a whole range of things. Somebody who, if you want a question answered, and he's prepared to answer it, he will give you the right answer, and probably very quickly too. This evening we're having a talk on amplifiers and distortion. This talk is part of a series looking at sound reproduction at the amplifier end. Last year we covered microphones, and we'll cycle through. But this evening we're going to have a look at amplifiers and distortion. Get all your questions ready, and I'll hand over to Ed now to give a talk on one of his hit subjects. Ed Cherry, make him welcome.
Thank you, people, for coming out tonight. It's a cold night outside, not quite as bad as it was a couple of nights ago, but it's nice to have you here. Now, I want to talk about feedback and amplifiers and distortion. And there's a broad summary of what I'm going to talk about tonight. I'd like to talk a little bit about the invention of feedback. You all know about feedback and what it does, but it would be nice to go back and see why it was invented in the first place. And I'm in a almost unique position in that regard, because I worked at Bell Labs and knew some of the feedback pioneers. In particular, I knew Harold Black, who was the inventor of feedback. So I can talk that with some reasonable background. And then we'll talk about the effects of feedback on distortion, how much it produces distortion, what else it does. And then we'll go sideways to something that's new and perhaps a little bit challenging. I think people like to hear something new as well as something that they know well at a meeting like this. So we'll talk about how much feedback you can apply to amplifiers. This was the problem of the Bell system back in the 1920s when feedback was invented. And then we'll flirt a little bit with stability. I'll remind you of a few things there. And then we'll come to the last two topics, which Graham rather asked me to talk about, some of the controversial things. And I'd like to say at the beginning, it's really unfair to talk about these because Ottawa, the man that was the originator of both of those two, is not here to defend his position. So you are hearing one side only of the story. It means it's a prejudiced side. I shall do my best to present it impartially and fairly, but there is nobody here to defend the other point of view. Now, both of those two are things which I believe are not valid distortion mechanisms. But rather than end the talk on a negative note at the end of the evening, what I'd like to do then is talk about something which came out of that interface into modulation distortion, a positive note, something is a possible good way. Come in. Possible way of looking forward and measuring distortions in amplifiers. Okay, so the invention of feedback. I want to take you back to 1927 when the invention came about. American Telephone and Telegraph Company, that was the Bell system, or AT&T as it's known. And even in 1927, that was on the way to becoming by far the largest company in the world. In fact, at its peak, it dwarfed General Motors and Holden and all those things by a large factor. They were pushing technology to the limit. They were really aiming to give the customer good service. And they were inventing new technology all the time, new ways of doing things. And the remarkable thing about AT&T was that 50% of their capital was tied up in the copper wires buried in the ground. So they were anxious to do anything to reduce the amount that depended on copper and reduce the number of copper wires. And in particular, taking telephone conversations across America or around the world, they didn't want to send one conversation on one pair of wires. They wanted to multiplex many conversations on the one piece of wire. So 1960, I don't know the numbers for 1927, but 1963, in 1963 dollar terms, when a house could be bought for about $10,000 in Glen Waverley in Australia, the turnover of the Bell system was 10 to the 11th dollars a year, and those were 1963 dollars, not 2015 dollars. And Bell himself had introduced the policy of putting 1% of turnover back into research, which makes 10 to the 9 of those dollars. And the Bell Labs, with that they employed 10 to the 4th engineers and gave them each 10 to the 5 $1963 to spend. So it is no wonder that the Bell Labs produced almost all the notable discoveries in electronics from about 1927 up to about the early 1960s when the antitrust people broke them up. And the philosophy of Bell Labs was to dig deep and look for good solutions, lasting solutions, rather than look for a thing to make a buck for us tomorrow. And the prime example that I knew about is Shockley. He was hired in 1932 because some of the people in the administration thought there just might be something in those semiconductors, and the rest is history. But it took until 1948 till the invention of the transistor. So 16 years lead time was typical of what Bell Labs was prepared to put in when they had a cash cow like that feeding it. Okay, well now about what was the problem in 1927. They wanted to cut down on the number of copper wires in the ground, and they want to multiplex a number of different channels, voice channels in those days, a couple hundred hertz to about 4 kilohertz. And they knew how to frequency division multiplex those. They could shift them from there 0 to 4 kilohertz and stick them one on top of another in a frequency spectrum. They knew how to do that. And then they could put all those through the one telephone wire or one intercontinental wire and receive them at the far end and separate them out again. So that was the object of the thing. Now, I'll put these next two slides in to frighten you. Definitions of non-linearity. You know about power series representations of non-linearity, the top equation up there. And then we can talk about incremental gain, which is the rate of change of the output with the input. Then the small signal gain, which is that coefficient A0 out the front of the whole thing. And then if you go to something that's manageable, you go to the soft non-linearity, we throw away everything past the cubic term and hope that's a realistic representation of what actually happens. It is actually remarkably good. If you look, say, at the 4th order term up in the first equation, you find if you apply a sine wave to a 4th order non-linearity, it turns out that generates far more second harmonic than 4th harmonic. So keeping just the 2nd order term is not a bad approximation. And the same applies to the 5th harmonic, which I haven't got up there. That generates 5th order term in the power series, that generates principally 3rd harmonic. So keeping the x cubed term in the bottoms there. But as I say, that's to frighten you, but this one will frighten you even more. People did know what was going on when you put sine waves into non-linearities. So if you take just that simple case in the first line where you put in 2 sine waves and you apply it to that small signal soft non-linearity, the resulting output is all that goddamn awful mess there. And the important things that come out of it are these two down. Back again. That's the one. These 2nd and 3rd order intermodulation. Everybody knows about harmonics, but you get sum of the two frequencies and the difference of the two frequencies, and twice one frequency plus or minus one of the other frequency, and down the second line you get twice the first. That's now omega 2 and omega 1. They swap the 1s and the 2s, so you get twice the second frequency plus the first, or twice the second minus the first frequency. Okay, we know all about those, I guess. You've seen things like that, but there it is in all its glory. Now, if you look at then what happens when you have your multiplex channels, that's however many telephone conversations can be mixed together in one of those frequency division multiplexes. Then we get twice that frequency, you get the 2nd harmonics, and 3 times that frequency, you get the 3rd harmonics. Not particularly interesting. And then the 2nd order intermodulations, which are in a band there that's centered about 0 frequency, curiously, and another band there that overlaps with the 2nd harmonics. And then you get the 3rd order intermodulations. And look at this one here, it lands right slap bang in the middle of the signals that you're trying to transmit. So the intermodulation, the mixture of 2 channels there, lands right in the middle of where somebody else's conversation is meant to be. And therefore the mixture of those 2 conversations can be heard in the channel that you're trying to use. So intermodulation gives a breakthrough of one channel into the other, and it's all a consequence of the cubic terms, the odd order nonlinearities in the amplifiers. Now this was perfectly well known back in 1927 when feedback was invented. The question was, how can we get rid of those odd order, 3rd order in particular, intermodulations? They knew about push-pull operation, but that only gets rid of even harmonics, doesn't it? No good to us. There were clever other circuits invented, but again, none of them reliably got rid of the odd order intermodulation products. So there was the problem. What can be done about it? I should say, incidentally, that with your mobile phones today, this is the same problem that goes on you get with mobile phones today. It's the odd order intermodulations that are the bugbear of mobile telephones. Okay, well then one sunny day, sailing across from New Jersey, Hoboken, into West Street and on Manhattan, where the Bell Labs were located in those days, Harold Black had an idea. There is the reproduction of his famous diagram, which he wrote in the corner of a blank page in the New York Times. He had that idea flanking cars. Well, there it is. You've seen that, but here it is in a bit more. So we have the forward path, the amplifier without feedback, if you like, feedback taken around it. We subtract the feedback from what's going in to produce an error signal and what comes out there. And the overall gain, the ratio of the output to the source, I call it, rather than the input, output to the source, G over 1 plus GH, or mu over 1 minus mu beta, which Black had. And the lovely thing is that's 1 over H multiplied by that factor there, and if that GH, the loop gain, is large, 1 over a large number is 0, so that whole bracket there simply becomes 1, and the overall gain is simply determined by that network there. That's the beauty of what we have promised. So, if we then look at applying feedback around a nonlinear circuit, so here we have the nonlinearity, a representation of an amplifier where there's a linear bit and the distortion is added in at the output there, and the feedback comes round as per normal. We find that the signal output remains as the normal expression, but the distortion at the output is reduced by this factor 1 plus loop gain. Okay, now you all know all that. You've seen that many times before. Now, that unfortunately isn't quite what happens in real life. If you apply feedback around a nonlinear amplifier, you don't find just that the feedback, the distortion drops. You find new components of distortion are produced, and you find that the frequency dependence of the gain of the amplifier, the poles and zeros, which we haven't written in that anywhere, these play merry hell with it. And the question is, how much is the feedback actually reduced in real life? So here's an experiment where what we, hang on, one more we go down. I've got this slides out of order. No, we're not. This is it. We've made a nonlinear feedback system where we've got the nonlinearity put at the end there, plus a linear gain ahead of it, and a feedback around it. And we've chosen that feedback factor so that as you vary the G there in the block there, that varies also. The overall gain remains constant as 1. So we're comparing apples with apples. We say as we put more feedback, but keep the gain constant, what happens to the distortion when we have a constant signal going in? And here's what happens. The original nonlinearity was this simple parabola coming around there, and which stops at the turning point of the parabola. You don't get the other half that you know about there. And if you were to put infinite feedback on it, then you get this dead straight line down to the point where it clips, and then nothing thereafter. But at some in-between value, and I've just drawn the case for loop gain of 1, which lies nicely between those two, you get some other curve, the grey curve in the middle there. Now, without the feedback, we were exercising the nonlinearity from that point up to that point. But with the infinite feedback, we're exercising it from a different point, way down there, up to way up there. When you apply feedback around the nonlinearity is not exercised to the same extent, even if you try to keep the signal amplitudes. You can think of it that if you put a sine wave in and it's got a nonlinearity that stretches the top half and compresses the bottom half, okay, the operating point goes up into that stretched part of the characteristic and never gets right down into the bottom part down there. But if you put feedback on and make it behave more nearly linearly as an oval, it never goes up into that top part, and it gets pushed further down into that curvy part down the bottom. So that the idea of simply dividing the harmonics generated by the nonlinearity, dividing those by 1 plus loop gain, is simply not the right answer. And here's a way that we can find out what does happen. Now we've done it with the forward path gain split into 2 parts, and we'll say that those are linear. We'll put the nonlinearity in the middle and the feedback as before. Now we're going to move that one up to the top of the screen and put a new drawing at the bottom. So there's the first picture as it was, but now we're going to inject an anti-distortion ahead of the non-linearity. You can imagine that there is something you can put in there. I don't know what it is, but maybe we could calculate. If we put up the right anti-distortion in there, the result would come back to an undistorted signal at the output. Think of it where you've got the non-linearity that stretches that side and compresses that side. What you need to feed is a bit of anti-stretching on this side and a bit of anti-compressing on that side to make up for it. And then we move this up to the top, so the top is the same and we've got to the new picture at the bottom. Because this block here is linear, you can move that one back to its input. And this still is exactly right. All you need to do is divide by the gain of that first block. And then moving them again, we can actually then move it from there where it was right back to the very input of the whole thing, because again those subtractors are linear. So if we put anti-distortion in there, we'll get an undistorted output there. And then the clever bit. The gain of the system, with including the feedback, because it's a decent feedback amplifier, it's practically linear. It's not quite, but it's practically linear. And therefore, to a very good extent, if you were to put the same anti-distortion in at the output after dividing it by the gain of the system, there's a G1 that comes from there, there's the H in the bottom line because that's the overall gain of the system. If you were to do that, you'd get, well, ideally it would be undistorted output. It's going to be almost undistorted because this is just not quite linear, but it's very nearly linear. So there is an almost undistorted output from the system, but there is the output from the amplifier itself. You just have to subtract off what you've done there. The distorted output is simply going to be, subtract that one there, neck there. And continuing on with that, get that? You could then say that the system there is very much like having the linear amplifier with that distortion injected back at the input. But you notice it's got a minus sign there compared with the plus sign which was in the previous slides. So by injecting an anti-distortion right at the input of the amplifier, you can get back to what the distortion of the amplifier should have been, and that anti-distortion is calculatable back from that original non-linearity, what you would have needed to put in to get an undistorted output from the system. What have we done there? Yeah, that's just to remind what is that. If you know the anti-distortion you need to put in there, then you move it to there, that will give you the distortion at the output. Easy as that. And this enables you to work out what's going to be the effect of the frequency response of the amplifier. There's a conjecture that says that if you have, say, a dominant pole in that block there, that's going to tend to filter out the distortion that's generated by the non-linearity, so therefore it does better than you might first have thought. Whereas if you put a dominant pole there, well, you need to think about that one a bit. But the lovely thing is that you see that distortion referred to the input involves only the gain ahead of the non-linearity. That sounds a bit of a non-intuitive, doesn't it? Why ever doesn't the gain of the last stage of the amplifier come into it? Let's put that one on notice for a question time, but that is the right answer. And if you think of signal-to-noise ratio in amplifiers, the only thing that the noise referred to an input of an amplifier depends on is the gain that appears ahead of the noise. It's a bit like a signal-to-noise calculation. We'll come back to that one, that's rather than labouring it now. Okay, so as far as the people were concerned at the Bell Labs, they wanted to get as much feedback as they could around their amplifiers to reduce the distortion as much as possible. And you all know about Nyquist diagrams, those funny, I always call them snail-shaped things. And Nyquist, back in 1932, derived this result there that in simple terms, that the thing must not enclose the critical point -1. The number of times the Nyquist diagram encloses the critical point is the number of poles in the right half of the S-plane. So by 1932, if they could measure the gain in the phase of an amplifier, they could say whether it was going to oscillate or not. But what they wanted was to get the maximum possible feedback. And all the early experiments, you tried to increase the gain somewhere, but the result was the phase shift went somewhere else in the wrong place. And it seemed to be a law of diminishing returns. what really was the limit to how much feedback you could apply. And this is where Bode came in. Oh, sorry, there's your Nyquist diagram that I should have shown you earlier. Yes, you all know about Nyquist diagrams, don't you? And you know about the gain margin and the phase margin. The phase margin is how close the gain can get to 180 degrees at the point where the loop gain is falling through 1. And the gain margin is how much the gain is less than 1 at the point where the phase shifts 180 degrees. I think that diagram might be wrong, isn't it? Shouldn't that point there actually be on, that curve should be at that point there. Anyway. So coming back now to what was the problem. We want as much feedback as possible over that bandwidth. That's where all the signals of interest are. We want to cut down the amount of, we want to reduce the non-linearity, the generation of intermodulation products just in that band there, that lot of stuff there. We don't really care about what those ones there do because they're out of our channels. They're not going to come back out onto someone's telephone line. Same with the harmonics. The only one that matters is that third order intermodulations. Okay, so this is the problem that we've got. We've got a bandwidth over which into which all those signals have been stuck together. We want to get the maximum possible loop gain, which is the difference between the overall gain and the forward path gain. The forward path gain drops away at high frequencies and drops away at low frequencies. This side is not very interesting because you can always get bigger coupling capacitors if you can make all them. You can shape that one whatever way you like. But the high frequency region was the one where they seem to be running into limits all the time. The amplifiers always oscillated at high frequencies if you tried to apply too much feedback to them. Okay, now here's another one to frighten you. Bode produced a relation between the gain and the phase. So if we knew the rate at which the gain was falling off, we could work back to what the phase must have been. All the fiddling in the world is never going to beat the limit that this equation gives us. So what it says, the phase shift at some frequency, all right, first thing is an integral over all frequencies. There's a contribution from every frequency there is from 0 to infinity. But those contributions have a weighting factor there, and that weighting factor goes off to infinity at the frequency you're trying to evaluate and becomes quite small away from that. So the thing that matters most in that result is whatever the gain magnitude is doing at the frequency where you're interested in the phase. And what is the relation? It's the derivative of the gain magnitude with respect to frequency on logarithmic scales. It's a logarithmic definition. That's why you have Bode plots these days. You have frequency on a logarithmic scale, gain on a logarithmic scale. The gradient of those is that's that term there. So looking at that if you've got a gain magnitude function, which just happens to be that, and if we want to know what's the phase shift going to be at that frequency there, all right, there's a contribution from there, there's another contribution from there, and there's a contribution from there and there. Contribution from there is very small, from there it's a bit bigger, and that's the one that gets you. That's the one where that weighting factor goes off to infinity. So the phase shift is predominantly determined by the gradient of the curve in that region there. And you knew that, I'm sure, didn't you, most of you? Well, what does the mean by gradient? I hate jargon. I hate computers because these are all dressed up in jargon. The computer experts talk about URLs and something or other, and I didn't know what they mean. Now, when you talk about a slope of 20 dB per decade, how many of you realise that simply means one thing is inversely proportional to the other? 20 dB per decade simply means inverse proportion. And if you have 40 dB per decade, how many realise that actually just means an inverse square law, like gravitation and electric fields and everything? Why do these coots dress them up in jargon like dBs per decade when that's all it means? All right, so if we plot the gain as numbers and the frequency of numbers on logarithmic scales and take the gradient, we can see what the phase shift is going to be at those frequencies. Now, there's one final thing. It's again at Bell Labs. Now we have Bode's relationship, which tells us the relation between gain or the rate of change in gain and the phase shift we must have, what can we do about it? And Llewellyn and Peterson, back in 1941, they produced this remarkable result that the high frequency response of the amplifier, remember the high frequency response, the gain bandwidth product, GM over C, they were able to show that GM over C for any tube, or for any FET, or for any BJT, came later, all of those are limited by the time it takes an electron to cross the device. So in a vacuum tube, it's the grid to cathode spacing. The closer you can put the grid to the cathode, the greater will be the GM over C. For BJTs, the narrower the base, the faster they will go. And for FETs, the channel length. Again, it's that which sets the limit to how fast these will go. In the case of the vacuum tube, there's the actual intrinsic capacitance within the device, but also the leads come out through those glass pinches at the bottom or out through the base, and there's capacitance there which adds to it, so that you can always have extra capacitance beyond what is in that formula there. But the intrinsic irreducible capacitance set by the physics of the device is set by the transit time of electrons. So the consequence of this is that if you look at the gain on log scales, and the frequency on log scales without any of these dBs per decade and things that just make it complicated, if it's a single stage, gain has to lie to the left of a proportional line. If it's a two-stage amplifier, it has to lie to the left of an inverse square law. If it's a three-stage, it has to lie to the left of an inverse cubic law, and whatever it is. So that's the final bit in the puzzle of working out how much feedback you can apply to an amplifier. So this is what we're going to try and do. We're going to try and get the maximum feedback there over that bandwidth there. And we're concerned with how many tubes we have, how many transistors, how many FETs, because that's going to set the gradient of that line there, like it or not. Now, to answer the question of what is the maximum feedback, that's a little bit tricky. I don't think it's a thing for a public lecture. But we can answer a related sort of question. We could ask, what is going to be the phase shift at that frequency there? Remember, Nyquist had a diagram. We have to keep the phase less than a certain amount. What is the phase shift going to be there? How's it going to vary depending on the number of tubes we take, knowing that this point where the gain goes through unity is, that's a constant, that's the GM over C. So let's look at this. If we have two stages, like down the bottom here, each stage has so much gain, and the asymptote goes down there. For each stage is at a single unit of slope, and the two stages will have the, like so. What's the phase shift there? Okay, it depends on the proximity of that break there and that break there. If we go to the case of three stages, now you need less gain per stage to make up the total, and that corner frequency has moved out relative to that one there, in accordance with Llewellyn and Peterson. So that one contributes less phase than that one contributes, but we've got three of those now rather than just one or two. So is three smaller phase shifts worse or better than two larger phase shifts? And if you go to four stages, the same again. Now that's only got to have the fourth root of the gain. That corner has moved out further still, but there are now four breaks there, each of those contributing there to the phase, which is going to give us the least phase shift at that frequency there. Well, that is a solvable problem. You can see that what the answer, well, you can see that it has an answer. The answer might be a little bit subtle. But here is the right answer to the question of the maximum amount of feedback. So there is the highest frequency, there's the corner. We want the free gain loop gain to be constant up to there. What we do is we put our, however many stages it is there, with the gain asymptote passing through that, we level it off, and that's the gain margin. That's how much you want the gain to be less than the demanded gain at the point where the phase shift is increasing. And then this gradient here, that from Bode tells us, that's going to relate to how much phase shift, how much phase margin we want. If we want 90 degrees of phase margin, then that can't drop down at faster than a single pole rate. If you'd accept 180 degrees, and you'd be damn fool to do so, then this could come down at 2 units of slope, and probably 45 degrees and 1.5 units of slope is about the right thing there. So we know that gradient, we know that frequency. What's going to make that line as high as possible gives the maximum possible loop gain. And the answer works out surprisingly as that the optimum number of stages is the natural log of the demanded gain. Everything else drops out. One of those remarkable results. So if you want a gain of 20, who knows what the natural log of 20 is? No? It's almost exactly 3. So if you want a gain of 20, then 3 is the right number of stages. If you want a gain of 55, how many stages would that be? Come on, take a guess. 20 times 2.7. 4 stages. So the natural log of the number of stages is the demanded gain. Natural log of the demanded gain. Again, natural log of the demanded gain is the optimum number of stages. Well, Bode spent half the book proving that, but that is the final result. Okay, well, let's leave that as if I said I was trying to frighten you. We'll now just get back to something that's easier. We've now shown how much feedback can be applied. Let us now see what the arguments are against applying too much feedback. Back in 1970, Tyler published this famous paper, which he conjectured there was a new distortion mechanism in transistor amplifiers, transient distortion in transistorized audio power amplifiers. Okay, now this is something like the model that he used for it. His power amplifier has gain and gain. Both of those are supposed to have no poles or zeros. And he's lumped all the frequency dependence as a single dominant pole in there. And he's got his feedback around it there. And then he's put a preamplifier in front of it, which gives a bit of filtering of the signal before it goes into the amplifier. And just to keep things easy, I've normalized the gain of that to 1, so that when you're talking of mid-frequency signals, you put a volt in there, you get a volt there. So keep the gain out of that one out. Now these are some of the waveforms that you find. If you put a step into it, at the source, okay, then after the preamplifier, which has a little bit of high frequency filtering, instead of going up like that, it's going to go smoothly up. And there it is as an exponential there. Okay? And if you look at the output for the amplifier as a whole, it takes a little while to get going, then goes up to the value there. And if we look at the error signal, it's this one which goes up, starts off initially following up the input after the preamplifier, but then it sags away as the feedback gets going, and it finally goes back to the equilibrium value, which is 1 over 1 plus loop gain of the input. Right? Now you notice that there is a large overshoot in the error waveform, and Tyler's theory was that if that overshoot drives the first stage of the amplifier into clipping, then you've got a real problem on your hand. You've got a distortion mechanism on your hand. So this was the model he had for doing it. Here is his audio amplifier. His power amplifier is the end of it there. Here's your feedback. These are the various poles in it. And there's the preamplifier with, he actually put 2 poles into that to make it a bit more complicated. And then we look at the waveforms. Okay, if everything is linear, I'll go back. He's got the option of putting in some diodes there to introduce the clipping of the peak of that overshoot, the error waveform. So if we look at the system without the clipping, you can see there is the step at the input. Here is the input to the amplifier, that's what I've called the input. He's drawn these to different scales so they don't look quite the same. The gradient there should in fact be the same as the gradient there, but this one is drawn on a bigger scale. There is the overshoot and decaying back again. And there is the output, and it's not very obvious, but there is in fact a little delay before it gets going and it smears its way up there. And then if you put in those diodes and get the clipping in the first stage of the amplifier, that and that looks the same, but this one you can see the overshoot which went up there has been clipped off. Okay? And therefore the output waveform looks substantially different from what it did there. And his test was, what happens if someone is playing a nice little flute, nice little sine wave with a flute, and someone whacks the big bass drum? And that's a bit like the situation of putting in a combination of a sine wave and a step. So here he's got sine wave and a step going in. And there is after the preamplifier we have lost a bit of the bandwidth. And there is the clipping, much as per there. But look at the output waveform. The flute has totally disappeared during that time of the clipping. So that was what Tyler called transient intermodulation distortion. Now, are we talking familiar things? Do you remember that one? You were part of that? That was the theory that he adduced for it. Now, these are my paraphrases of what he concluded. And again, I say I am aware of you're only hearing one side of the story. So this is my version of what he said. Okay, it occurs if the open loop response of the power amplifier is slower than the response of the preamplifier. The condition under which that overshoot occurs is if the bandwidth of the preamplifier is greater than the open loop bandwidth of the power amplifier. He's right on that one there. And then there has got to be an optimum amount of feedback. If you have too much feedback, then that overshoot is going to be greater, and that's going to increase the incidence of TIM. But if you don't have enough feedback, then the ordinary distortion gets better. So the conjecture is that it's got to be an optimum amount of feedback, in which the overall distortion is less. And then finally, that's the lag compensation techniques, the things that we all use in op amps and whatever, that these are inadvisable because it's the result of that lag compensation, that dominant pole, which results in that overshoot, which, if it clips, is what causes the TIM. Now, I was one of the first people to say that he was wrong on that, but I was not alone on it. Tyler visited Australia in 1975 at Sydney Audio in Sydney IRE convention, and I met him there. Now, there were a number of other people who said that he was wrong. First of all, Greg Campbell and Kishore Datki, friends of mine, colleagues of mine at Monash, they are very great contributors to everything that I have said. And then other people, Jill Singh and Rigby and Olsen, I don't know. Bob Cordell at Bell Labs is someone who I did know. Then Peter Gard in Sydney. Recognise his name? He came from Melbourne, a Monash student. Actually, was one of my very early graduate students. He in 1978 said some rude things about them. Young Stevens and Todd, 1979, I don't know. Dick Small, everybody knows Dick Small, the Teal Small loudspeaker theory. He didn't actually go into print criticising Tyler, but he was saying all kinds of useful and correct things in the wings behind. And I think he was certainly influenced by him. So I was not alone in saying that there's something wrong with Tyler's theory. Okay, now what was wrong with it? First of all, that model of the operational amplifiers, everything was normalised. You couldn't see what anything actually meant in terms of real frequency. What frequency was the flute? How large was the wagon for the big bass drum? We'll come back to normalisation in a moment. And then the second thing is he was confusing between overshoot and overdrive. That error waveform, up and over. But if that peak stays within the dynamic range of the first stage of the amplifier, there's no problem. We'll have a look at that one later. But maybe this next slide. Yes, if you look what happens here, as you increase the loop gain, as you increase GH there, what happens is not that that peak gets bigger, but the final value gets smaller. So it's the end of it getting smaller rather than the peak getting bigger. It occurs as you apply more feedback to an amplifier. And that is the fundamental thing that is wrong in what Tyler was saying. It's not that the peak gets bigger and therefore is more prone to clipping. It is that the final value, which is practically zero anyway, gets even closer to zero as you apply more feedback to it. And if you look at the waveforms here they are drawn to a larger scale. So there is the sine wave, that's the flute, and the wang of the big bass drum. There is the thing clipped off. Now look closely at those waveforms there. What do you notice there? What do you notice there at the beginning? It's slewing even before the thing has occurred. So there's something else non-linear in his models. He was pushing the thing sufficiently hard and something he hadn't expected was going non-linear. And second, this one's a bit subtle, but can you see there? That's got a downward slope on it. Okay, so there's some other low frequency effect taking place there which is not accounted for, which his model should not produce. You can begin to, Yeah, okay. Look, that's enough. There are two obvious faults that are wrong in his model. There's something wrong in the model that produced these. There are two instances of it. And the normalization, that's the same slide, but to produce the thing, the flute had to be at 600 kilohertz.
Not a bad flute.
And the bass drum rise time had to be 200 nanoseconds. So if I say the trouble with his normalization, he did not consider what the results meant for real audio amplifiers. If you want to listen to a 600 kilohertz flute and someone has a bass drum with a 200 nanosecond rise time, you might have something. But otherwise, it's not going to occur. So that is the my summary of what is wrong with transient modulation distortion. There basically is nothing. There is no problem with a sensible design of an amplifier. So there's his front cover again. What he said was transient distortion in transistorized audio power amplifiers, and in fact, it's wrongly classified. It's not a transient distortion. Transient distortion is what we talk about resulting gain and phase variations, deformation of pulses in old-fashioned analog television waveforms. Transient distortion had a perfectly accepted use since at least 1948. It wasn't a new phenomenon. It was well known in 1970 as slewing. You all knew that sine wave. That was slewing. There were analyses of it as early as 1946 by Thomas and by Flood in 1953, and then the definitive analysis was by Solomon, Davis and Lee in 1969, before Tyler's 1970 publication. So it was not new, and then it's not restricted to transients. It happens with sine waves. You notice the slewing of the sine waves quite independent of the trend. It was not restricted to transistorized circuits. It happens with vacuum tubes, which is what Flood and Thomas were talking about. And it's not restricted to audio amplifiers. It happens in op amps, as you would know. So what can I say? Other than that, I think Tyler misled the audio world. And it's easy enough to make sure that you don't get TIM occurring. Forget about all the second half of the amplifier, but just look at this first stage here. All you need to make sure is that the first stage of the amplifier, remember the waveforms, there's this step going up and then the error going up like that, but this peak is less than the step that goes in. If the first stage can accept the maximum signal amplitude, then there is no problem. In this first stage, we've got a diff pair with 300 ohms and feedback resistor. And this was at 15 volts and 4.7K, that's about a 3 milliamp tail source there. So there's about 3 milliamps, 1.5 milliamps in each of those transistors. There's a current mirror at the top so that the output you can get there is plus or minus 3 milliamps if you've got a 3 milliamp tail current there. Plus or minus 3 milliamps, that's 6 milliamps peak to peak. The gain is set by that resistor, 3 milliamps per volt. So that would set 2 volts peak input. An amplifier was only rated at 0.4, which got a factor of 5 safety over. There simply is no issue with TIM in a halfway competently designed amplifier. Now, Tyler was also the man that produced this amplifier loudspeaker interface distortion. And again, I'm sorry to say that I believe he is wrong on that. Same people whose names I put up before, I think, would all agree with that. This one never got to the stage of being published in a professional journal. It was presented at an AES preprint. I've forgotten what year that was, and something about it was done in Wireless World in about 1980. Okay, now here's the theory of it. Loudspeaker, the driver, it's an electromechanical system. If you give it a push, it will vibrate depending on the damping of the enclosure and whatever. As the cone moves, and it might move because of the current that you've pushed through it to make it reproduce sound, or because if you put a step into it, then it's going to keep on moving because of its inertia, or just maybe because there's incident sound on the cone, either from the room or from the inflection enclosure. So if the cone moves, there's going to be a voltage induced in the voice coil. And in a feedback amplifier, that voltage coming back goes back into the input stage of the amplifier through the feedback network. Again, has the possibility of intermodulating with the input signal. And if you have more feedback, more of that signal, motional EMF from the loudspeaker, finds its way back to the input. And it's going to be particularly bad when you've got common emitter BJTs or pentos as the output stage of your amplifier, because that provides no damping on it at all, nothing to absorb any of that backwards coming power. So this was, again, a simplified version of the Taylor's model. His amplifier, emotional EMF over there, the voice coil resistance. You know from Teal small theory, really the only element of the driver that counts, other than the mechanical properties, and the only electrical property that matters is the voice coil resistance. Neville Teal said that of the power delivered to a loudspeaker, something over 85% finishes up as heat in the voice coil resistance. Okay, so the EMF finds its way back, particularly if that resistance there is large, like for a pento, finds its way back down here, back into the input, intermodulates with that, and obviously the more feedback you get, the more greater is the chance of intermodulation occurring. There is the thing drawn a little bit more respectably. The amplifier is the same, but now we've got the voice coil resistance, and then this ideal transformer that Dick Small and Neville Teal introduced, and then the mechanical properties of the cone compliance, which is inductance in this model, and the mass, which is capacitance. And this transformer here has a turns ratio, not ordinary turns, but B, the flux density, and L, the length of the wire in the voice coil. The force on the cone is the current multiplied B by the field strength and the length of the wire in the gap. And equally, the voltage, the velocity here, there's a voltage which comes back there is BL times the velocity gives us the voltage that is induced coming back there. All those standard Teal small equations. So there is the mechanical resonance of the driver. This converts it back to electrical things, and the voltage associated with that finds its way back there. Now, can you see the fallacy that if you apply more feedback, there's a greater chance of intermodulation? What's the fallacy of that? How do you apply more feedback to an amplifier? How do you apply more feedback? What do you change?
You get a increase the amount of feedback that you're giving, basically, so reduce the gain of the closed loop gain of the amplifier.
Yes, but what, in practical terms, what do you change when you put a bit more feedback around an amplifier? Do you tinkle with that, or do you tinkle with that?
Phase shift.
Yeah. But what I want you to then looking for is someone to say you normally leave the feedback network pretty much alone because that sets the gain. You get your feedback, your increased loop gain by putting more GM into that model there. So that actually stays constant. And so irrespective of how much GM you've got there, what comes back is independent of the amount of feedback that you've got. So again, that model seems to be quite invalid. It simply isn't what real life is about. You don't increase feedback by changing feedback resistors. You put more gain into the forward path next to the transistor. There. Well, that's a fallacy, and here is going to something which I think is useful to finish off the talk. An idea that arose out of that Atala paper, how to test the distortion in an amplifier. And what we've got is a stereo amplifier with two channels and two frequencies going into the inputs. Said 5 and 7 going in there, and we've connected the load resistance not to ground but between the channels. So the two outputs are going up and down at different frequencies, and a resistance which is not the ordinary load resistance but square root of 2, 1.5 times it near enough is the right value to use. And look, see then what happens. If you test an amplifier with a resistive load, just a simple resistive load, the output current and the output voltage are always proportional. The operation is entirely along that line there. If you give it a pure capacitance load or a pure inductance load, the voltage and current move around a circle there. The peak of voltage, peak of current occurs at the zero of voltage in the capacitor, and the peak of voltage occurs at zero current, and peak of current occurs at zero voltage. With a pure capacitance load. And if you have an RC load, then the thing goes round in an ellipse like this. Now, if we're going to test an amplifier, mindful of what we've said about stability, and mindful of the fact that protection circuits might operate prematurely if you get up into some of these regions here where this, or this region here where the current is in the wrong direction for the voltage. if you want to test an amplifier thoroughly and make sure it really is stable for all modes, what we have got to do is an enormous number of these ellipses, different values of load resistance and different values of capacitance and different frequencies. Yeah, that's a major job. Can we invent some way of testing for everything in one go? Well, Greg Campbell's idea was the picture of the previous slide. You apply the two different frequencies to the amplifiers like so, and it turns out that the operating current and voltage for each amplifier is a Lissajous figure, the ABC television sign, and it fills up the whole of that parallelogram there. So it goes way back into this region here where the capacitance loads would go, way up. It covers the whole of the range there. We've tested the amplifier way beyond what you could do with a resistance load or a capacitance load, and of what you can do over a whole range of frequencies. So that's a good way of exercising the amplifier over the whole of its output plane. And if you look now at what might happen, remember those are the two frequencies we're putting in, 5 and 7, and back to those frightening slides at the beginning, you get second order intermodulations there and there, and third order intermodulations there, 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 and there. Those are the frequencies that are involved. Now let's apply this to a real case. Let's test an amplifier at mid-frequencies. So we put a kilohertz in there, we put 1.4 kilohertz into the other channel, and we look for the second order product there and the third order product there. Nice sensible audio frequencies, more or less in the middle of the mid-band range, way clear of any harmonics of the signals, way clear of anything that's going to confuse the issue. Very easy to measure those two frequencies there. And if you go to testing it at low frequencies, what we put in is 25 hertz and 35 hertz, and we look at 45 and 60. Again, nice frequencies in the ordinary operating range of the amplifier. And again, those are way clear from anything. The harmonics of that one, they would be at 70 and 105, is it? The harmonics of that would be 50 and 75. Don't blame on any of those ones there. In fact, these don't even have to be particularly pure waveforms, because the harmonics of those don't matter. We're not looking for those. And finally, your high frequency distortion, well, I've suggested 10 and 14 kilohertz might be the good numbers to put in. You look for the intermodulation products down there. So this seems to me is a very good way forward for testing amplifiers. You can test all aspects of the output stage, where it operates at high currents and low voltage, where it operates with current in the wrong direction, as we get some parts of a reactive load. It strikes me as a nice way of testing it. And I'd like to leave that with you tonight, to think about testing amplifiers that way. Is there something wrong with it? Well, I'd like to hear from you now, please.
You're testing the stability of amplifiers.
Yes.
What was the load? You had two amplifiers with a load.
Yeah.
What was the load that you used?
Just plain resistive load.
Just plain resistive load, the square root of.
Yeah, square root of 2. Because when one voltage is, if that one is positive, for example, and this one is positive but going at a different. Now let's go easy to see in this one. Is it? If the you can imagine this as you figure filling up that shaded area there.
Yeah.
It's going to test all of those where you've got current and voltage in all kinds of phase with each other momentarily.
So what you're saying is you can test the stability of an amplifier with resistive load.
I wouldn't like to say you can test it completely, but you can get a good indication if there's anything gross going to happen, like when the protection circuits begin to come in. If you put a current limit on the output transistors, that normally alters the response at that stage. If that comes in prematurely, that will show up on this test. Yes, please.
Is there a penalty for using bootstrapping in an amplifier?
Tell me more of the context that you wanted to use bootstrapping.
Well, it's on the top half of the amplifier.
Output stage, is it?
It's a fairly large electrolytic capacitor,
Yeah.
and I've been told somewhere in the past
Where's
that
that?
the amplifier won't reproduce pulses satisfactorily if there's a bootstrapping.
Well, this one's got a bootstrapped output stage on it. So there's the first stage that we talked about. There's the feedback network. This is something funny in the middle. Let's not worry about that. And there is the what you call it, the voltage amplifying stage. The transistor has its emitter up on the rail. There is the synthetic diode producing the bias, and here's your output stage with the first driver and the output stage, driver and output stage.
You know, I see the bootstrap cap there.
There's the bootstrap cap down there. Yeah.
Why did you put that there?
If you don't, what would be the alternative? What do you think is an alternative? The current source?
Yes.
No particular reason. I like this one. This better. I suppose it will take you closer to the negative output, right?
Yeah, it increases the output swing, but I think there is some kind of penalty for doing that. And I read somewhere a long time ago that it won't reproduce unipolar pulses very well.
Well, I guess that's right. Same as a coupling capacitor back at the input there. If you put in a funny shaped waveform, one which has if you put in a... Graham, do you want to say something?
I did.
Yes, please.
At low frequencies, you'll lose the benefit of that bootstrapping. So at low frequencies, you'll fall off having extra voltage available to you.
Yes,
Yeah,
but
depending on the size of the electrode.
But the frequency we've got there, the frequency where it stops is basically the time constant of that resistor and that capacitor. That's the main terms of it. So 100 mics and 1 kilo, and that's 1.6 hertz.
Professor, what ratio did you use 3.9K to 1K? Normally, a bootstrap is used 50-50.
Not in my designs. I don't have any basis for that. Normally wants a much smaller resistor. That resistor there appears in parallel with the input resistance of these transistors.
Yeah.
So therefore you want to get that one as large as possible. Putting a resistor in parallel with the transistor is equivalent to reducing the beta. You want all the beta you can get from your output transistors. Remember the input resistance of a transistor? If you've got GM, what's the input resistance? Beta over GM? Near enough.
I'm sorry, I can hardly hear everything.
I'm sorry. The input resistance of a transistor is beta divided by GM.
Sure.
So transistors with the same GM, you don't want you want the maximum beta. And if you artificially reduce the input resistance by putting something small there, then you're just throwing away beta from your power transistors. So my rule is to put that one as large as you can, and that one small enough, but it's not so small that it begins absorbing appreciable power from the output. Yeah. The output power comes back from, where is it, that way, isn't it? Comes back that way.
This is not really written in the information that I've seen over the last 30 years. It doesn't seem to be talked about very much. I can see your point, but it's never put forward by anyone.
Okay, well, do you want to write something?
Yeah.
Write a paper.
It's a good idea. I use the technique myself
Yeah.
because I find it sounds better, actually.
Yeah.
And I wanted to know what the reasons were, and you've just given them.
Well, my answer, bootstrapping is cheap. A transistor doesn't cost much, I suppose.
More reliable.
Maybe. It's cheap. It gives you the ability to swing right down to the negative rail at the output. You can get voltages at that point which are more negative than the negative supply rail. So you can drive all the way down, but you haven't got any corresponding effect on the positive side. So if you only want to produce signals that go one direction, it's great. There was an RCA design, 1970, 1960, I don't remember when. I think where they bootstrapped the positive side as well. They put another capacitor from there effectively round onto, well, that resistance there to move that side. But that mucks up all my things.
I should let you know that Hugh has designed amplifiers that include that facility, haven't you? Yeah.
I use
Double
two
bootstrap.
Can I
bootstraps.
Can I ask a controversial question, perhaps? Do you have any comments on the audibility of distortion in amplifiers here? No.
I'd have to say that I'm. If there is, I believe that if there is. If there is I believe there's perfect correlation between a non-linearity source of distortion and, if you have the mathematics right, there's a correlation between the non-linearity and the distortion that it will produce. And that's a different question from the one you asked. What about the audibility of it? No, I don't think I really do. People claim to hear extraordinary levels of distortion. I can't. I don't have golden ears. I don't. Sorry, it's not a very good answer. No, I don't.
No, that's fine. That's fine. Controversy.
Yes, I'm not prepared to go into that one there.
Maybe that's allied to listener fatigue.
Could be.
There's a question there. Yes, and then Rob.
Sorry.
Yes, please.
Do you have any comments on so-called current dumping methods of people like Atkinson and Walker?
Yeah. Nothing very helpful. Peter Baxendall gave what I thought was a fairly clever explanation of that. You're familiar with current dumping, I guess. We have a thoroughly non-linear amplifier in parallel with, or more or less in parallel with a nice little linear one. The non-linear one provides all the output current. Their outputs are combined in a bridge circuit, and if you balance the bridge right, then none of the distortion from one of them appears at the outputs. Yeah, so that's close enough. Peter's explanation was that when the I think I'd like to take that question on notice. I can't really give you when the dumpers come in, that their output resistance appears somewhere in that bridge circuit. And that changes the gain of the bridge from what is the actual output of our speaker to the feedback terminal back to the input stage of the amplifier. And the change in the feedback factor changes the demanded gain of the amplifier, and it changes it by just the right amount to make up for the non-linearity of the numbers. Now that's awfully hand-waving. I might be able to do a better job with a pencil and paper in half an hour. I don't think I can do better than that about the pencil and paper in half an hour.
There was an analysis that they published, and I think it was Wireless Worlds.
There's been various. There's the original Peter Walker amplifier, but the original article was remarkable in what it didn't tell you rather than what it did. It only told you the things you wanted to hear, and it was, I call an advertising blurb for quality. Peter Baxendall, I think, was the one who went closest to explaining what really did happen. I don't think that was ever printed in Wireless World. I don't think it was.
I can hunt that up, I think,
Yeah.
if you're interested. I can find one of the. There was a better explanation of that. There was a question up the back there.
Ed, in his very last written work, Peter Baxendall quoted you talking about problems in taking the dominant pole capacitor right to the output, and there was mention of capacitors to stop very high frequency problems in the output transistors and so on.
Yes.
Now I notice you've done it in this amplifier, and I wonder if this is later and whether the technology had changed since Peter died, or
I've always done it that way. That's a Cherry design, and I've done that since the middle section of it is 1970 something, but the output stage is 1960s. When were MJ802s invented?
So the poles introduced by all the transistors after the voltage amplifier are all just totally irrelevant, are they? It's just too far away.
Totally is a bit strong, but very nearly.
Can I comment?
Yes, please.
That output stage configuration with the series inductance and the shunt capacitance below it gives you a second order low pass filter to keep in high frequencies out of the first stage. So it's very useful also for RF interference coming in on speaker.
That was Neville Teal's idea.
Yes.
Yes. Well, that was,
Would you own a Class D amplifier?
do I own
Would you own one?
I probably would. I don't think I do. No.
They are very cheap.
Speaking of RFI.
Yes.
Question.
I thought there was a question here.
I thought there was. No, I think he was pointing at something.
Okay,
Did you have a question? No. Rod, yes.
Professor, thank you for your book in 1968 and your 64 paper. I started my career with those. I saw
If you may interrupt you there, sorry, the book has been republished online by University of Turin, if you want to get a copy.
Oh, lovely. I haven't got mine yet signed.
No, it's nothing like the original.
I remember one of your presentations, I think it was for IEEE or IEEE, where you showed your nested feedback amplifier and a 10-watt valve amplifier with a properly constructed setup, where people literally couldn't tell the difference between the two amplifiers.
That's certainly Mike.
For many years I ran a similar sort of experiment with my students in sound recording in a reasonably good studio, and I deliberately introduced clipping where I could show that there was 10% distortion, a linear amplifier that was frequency limited to 16 kilohertz and 100 hertz at the bottom end, and a straight piece of wire. And the students preferred the distorted clipped amplifier, then the frequency limited one, and last but least the straight piece of wire. So people cannot hear distortion, I
Well,
believe.
that's certainly, when Graham asked that question, I did some experiments, not extensive, but experiments with set up with where the obvious problems with switching between a piece of wire and an amplifier had been removed, and nobody could hear the difference. That doesn't prove it. To say you can't prove it, it's terribly done.
Well, none of my students picked it anyway.
Yeah, one of the things that we did at Bell Labs, this was in the very early days of picture telephones. Now this was analogue. Brainard and Ralph Brainard and somebody else, I've forgotten the names of the two, who did the research on what was the effect of quantizing noise, if you like, in a digital picture. So they quantized it to 8 bits or 6 bits or whatever. And before Bell Labs would accept their result, this thing had to be tested in every conceivable sort of program material with zillions of observers. Okay, they established what was the right limit, but my goodness, it was a fatiguing exercise. I was one of the guinea pigs, and I was fed to the back teeth at being shown pictures with various levels of quantizing noise in them. And I think that was the general result. If you're going to get a subjective test and get a result which is meaningful, you've got to get a captive audience that you can keep testing. To come back day after day after day, or actually week after week, so you make sure you get what one person really does think rather than what they thought on that particular day when they had a bad night before. Yes, subjective testing is terrible.
Do you think THD is an adequate way to assess the performance of an amplifier these days?
THD, no. What frequency are you going to choose?
Fourier analysis.
Well, if you go to total harmonic distortion, what frequency are you going to use for the test signal?
Well, it's usually at 1 kilohertz, but what I'm claiming now, even with CAD now, you can get an FFT of the products of the amplifier, so you know what harmonics may sound better than others.
Yes. Problem with, it's a bit like the original problem with the frequency division multiplex that Bell System started all those years ago. We hear from 20 hertz to 20 kilohertz, more or less. In my case, it's probably about 6 kilohertz at the top, and it rolls off before you get to there. But there is a band over which we hear distortion, we can hear. Now, if distortion products fall outside that band, I'd take some convincing that they affect the actual sound. So like the Bell System, we didn't care about the harmonic sort. The only thing we were worried about were those third order products that landed in the pass band of the inputs.
And that was intermod.
That happened to be intermod. Harmonics never fall in the test band, by definition.
Okay, any questions? All right, now's your opportunity. Well, I'd really like to thank Ed for taking the time, and also thank his wife for coming along tonight to give us some information on amplifiers.
We've been married 52 years and it's the first time I've heard him speak.
Is that
No, you did say I do on one occasion.
Yes, dear.
So tonight has been raising more questions for me, and possibly for you, to look at some of these issues a bit more scientifically and less perceptually. So I'd like to thank you, Ed, for taking the time for coming along and giving us a very informative session. Thank you very much. I'd like you all to join me in thanking